Hey, good afternoon and welcome to another GReTA seminar this afternoon, or as it is on the other side of the planet for Ricardo, sort of reasonably early in the morning. So I'm very happy to have Ricardo here today. So I just established that we've known each other for at least 10 years, or around about 10 years now, because he was part of a group in Edinburgh working with on Kappa, and I visited him a few times, and he came here to Leicester as well to visit us. The topic today is also inspired by that period of work. So Ricardo is no longer in Edinburgh. He's in a postdoc in Valparaíso now, living somewhere in the hills in the area there. But don't expect me to explain the geography of Chile to you now. So I would probably struggle with that. But anyway, so this is interesting work because it uses some of the specific features of Kappa and more generally graph rewriting for modeling biological systems, which imply certain constraints and certain sort of specific properties to do something that you wouldn't be able to do in a completely generic graph rewriting approach. Yeah, so this is really where a particular application domain determines not just interesting problems, but also solutions in providing sort of meaningful restrictions to the general approach, which then allow to solve these problems. So I'm very keen to see how that has evolved in the meantime. So yeah, please, Ricardo, take over from here.
Thank you, Raiko. So yeah, what Raiko says is important, and it will be important for the talk. The fact that the type or style or flavor of graph rewriting that we work with has a few differences with the more general graph rewriting setting. And here, the most important difference is that the nodes of the graph have a sort of interface through which they can interact with other nodes through which they can bind, right? And this, on one hand, limits the number of connections that any node can have, but also helps you have to have a guide through which you can, follow a homomorphism. So there's more restrictions that make this, as Raiko put it in one of his papers, makes these graphs rigid, right? That rigidity property is kind of important for what we're gonna do. And in particular, this rigidity allows this type of graphs to have the following property. You can substitute or change one graph for kind of like a set of graphs that map exactly to the same graphs in the same manner, so to say. So if you like, well, we will see examples where that will be more clear, I think. But that's an important property of our graph rewriting system. So one good thing about graph transformation, graph rewriting rules is that they allow you to express in the rule the minimum information that's required to express the change that is about to occur in a graph, right? You do not have to give us any kind of context The context is just given by the application, but the rule itself doesn't say anything about, or doesn't need to say anything about the context in which this rewriting happens. And in Kappa, we used to have this saying, don't care, don't write, which is basically the same thing, right? If you don't care about what is the state of a certain entity that is involved in the rewriting, or you don't care whether an entity that appears or a node that appears in the rewrite in the rule is connected to someone else, you just don't write it. And that's very good for managing certain kinds of complexity that arise, especially when you, I don't know if in other domains it happens as well, but in biology, molecular biology, organic chemistry, that's usually needed. And in fact, this kind of idea that, for instance, that atoms could be bound to anything appears in organic chemistry notation. I think even before there was any talk about graph rewriting. So that's good about graph transformations. We want that, right? We want that conciseness. And in fact, now talking about conciseness, that's also another important thing that I want to convey in this talk. That something that we are doing here, and something I'm concerned with in this kind of work, is the conciseness of the models that have to be written by hand, right? It's like, in a way, it's like software engineering, or you could say model engineering. You want to make your models concise and expressive, and for that reason, I like very much graph rewriting rules, and I think maybe you as well. So in these kind of settings that we work on, like for instance in organic chemistry or in biochemistry or in molecular biology, however, the rates of these interactions, of these reactions, of these rewriting rules depend on the context, right? It's really great that you can express things in like giving the minimum information that's required for the interaction to happen. But then on the other hand, at least in these settings, we know that the rate at which these reactions occur will depend on the context. Will depend here is just a list of different kind of factors that could influence the rate of a reaction in chemistry, organic chemistry, or molecular biology. For instance, the solvent, the cooperativity that might exist between different, for instance, protein subunits. And we will see an example of that in the next slide to understand what cooperativity, and it's an important source of inspiration here, because cooperativity, at least some people, some scientists believe, is really important in biology. Like, it's one of the main control mechanisms that exist at the molecular level. So we really want to have a tool which allows us to write concise models for these kind of settings, for these for the situations where there's cooperativity. Also, you know, when there's catalyst, or the temperature and pressure can change the rate of the reaction, the concentration of the participants of the reaction, the surface area, like the area of the protein or of the molecule that is exposed, right? Usually it's one part of the molecule that is the one that actually reacts with the other molecule, if there's any. And if that part of the molecule is kind of hidden by another part of the molecule, the reaction will happen more slowly, right? Because that part of the molecule that's hiding the active site, for instance, will have to move and give room for the reaction to happen. Also, in the case of DNA, you have transcription factors that can change the rate of transcription, which is a particular type of reaction. Or in the case of DNA as well, methylation can change also the surface area that's available. Or in the case of proteins, phosphorylation can change how ready a molecule is to participate or engage in a certain reaction. So now we will go to cooperativity, and I'll show you one of the models that exists for cooperativity. It was, I think, the second model proposed. It's called the sequential model, or KNF it's an acronym of with the surnames of the people that discovered or proposed this model. And here in this model, we have a, I'm sorry. We have a, for instance, a protein that have a 4 subunits. And these 4 subunits can be in one of 2 states, either the orange state or the blue state. And to these subunits can bind this ligand, let's call it this molecule. Yeah. So when this ligand binds, that makes it more likely that the subunit that is bound to it will change to the blue state. Once it changes to the blue state, now this blue state can spread through the molecule. And here, that's the cooperativity part, right? The fact that neighboring subunits like to be in a similar state, in a similar color in this case. So and you know, with the molecule that is bound to it, they have like a mutual stabilization. So once the color is blue, it's more likely that another ligand can bind to the unit that is blue, and also it makes it less likely that these green ligands will unbind, so stabilize. That's what's called positive cooperativity. There's also another type of cooperativity that's called negative cooperativity, in which case the binding of another ligand is or the probability of binding of another ligand is decreased by the presence of the first and so forth and so on. So 2 ligands make it even less likely that a third ligand binds. And of course, this network here is not complete. You've got plenty of arrows going outward, right? You could bind to a different subunit. Really, there's even small chance that any subunit will spontaneously change into a blue subunit. It's like all the possibilities, like a kind of multidimensional matrix. So if we were to write this model using the graph rewriting rule, we would need to specify at least how many. Well, there's two rewriting rules involved here, right? So one is the binding rule of the green ligand, and there's another one that is the switching of the color. Those are the 2 basic rules. And but the switching of the color in particular will depend, the probability with which it happens will depend on on whether it's bound to a green ligand or not, and also what's the state of the neighbors. So you have to count the neighbors, how many blue neighbors you have, and then whether you are bound to a green ligand or not, and that will give you your probability or your rate of reaction, your rate of interaction. So in that case, the number of rewriting rules that we have to write for the switching of the state of the color is proportional, right? It's linear in the number of neighbors that you have. You just have to count how many blue you have. Okay, so here we would like to separate concerns, because on one hand we have these two rules, right? The ones that I said at the beginning. So you have the switching and the binding, and the unbinding, which are the basic rules. But then you have to write by hand, usually, many copies of the switching rule for all the possible combinations that you have. And that's just to change the probability or the rate at which the interaction happens. So what I propose here is that we separate concerns and let the rules tell us what's possible, and let the energy terms, that I will talk about what they are and how they work in the next slide, tell us what's likely, right? What's the likelihood at which things can happen. So in the model that we just saw, we will have the two basic rules that I said, right? Switching and binding, and we will have these energy terms that here it tells us that whenever the green ligand is bound to the unit, then the blue state is preferred, right? That when we talk about energy, we usually take the convention that less energy is more favorable. So that's why there's a less than here. Here we express the idea that, this is wrong. It should be flipped, right? So this should be on this side and this should be on that side. So it's less favorable to be in disagreement with your neighbors, and it's more favorable to be in agreement. And finally, when there's no green ligand, when the subunit is free, the orange state is favored instead. So now we just have these energy terms, and we will let them generate all these possible combinations that we spoke about in the last slide or in the previous slide. Is that clear? Great. So how does this energy work? Well, we will have energy terms. T is an energy term. Epsilon T is the energy cost of that energy term. And we will write T of X to count the number of occurrences of the energy term T in X, right? Just the classical pattern matching that we do in graph rewriting. And we will define a very simple energy function that is just the sum of these over these terms, taking into account the cost of each term and the number of occurrences of each term. And we can write the same thing in vector notation like this, right? You have the vector of energy cost, and this would be the vector of occurrences of all the energy terms. And once we have this energy function, or we can derive through the standard laws of statistical mechanics, if you wish, this relationship, which is a ratio. It's a relationship that constrains the ratio of the rates of the forward and backward reactions or rules, right? So the logarithm of the ratio of the two is got to be equal to the difference in energy that is produced by the reaction or rule, and just right, taking it from here, we get this, right? You have the vector of energy cost, and here now you have the vector of how many copies of an energy term is created or destroyed by each rule. And this bit makes things a bit more difficult, right? Because now not any rule is good for us, right? We need rules for which this quantity can be in some way fixed. So we need to have rules that will always produce the same, that will always produce the same amount of energy terms and will always destroy the same amount of energy terms. Although there are a few options that maybe we should explore before. One classical option is called the Metropolis algorithm or the Metropolis-Hastings algorithm. And here, to satisfy this equation here, you pick a state X, then you pick a transition that goes from X at random, and you compute the difference in energy between the source and the target state, right, of the transition. And if the difference is positive, meaning that the energy of the target is below the, or target is maybe not the good word, right? Or the, no, well, if the energy of the target is less, no, sorry, is less than the energy of the source, then you take that transition, right? You go to Y, surely, with probability 1. But instead, if the difference in energy is negative, then you take the transition with probability e to the minus delta E, the difference in energy. That's one option. That, I'm sorry. That option has the good thing that we can just run it, right? But it has a penalty, which is that while you are running it, you have to be computing these differences in energy between the source state and the target state every time you want to take a transition, and that might be costly. And then you have another option, which is just enumerate all transitions. In the setting that we are seeing here, usually the state space is kind of finite because all rules are reversible, and you have a few constraints that make the state space finite. But usually the total number of transitions will be too big. So even though you could just take, every pair of states and compute the delta energy and store it somewhere, and then use that delta energy to choose a good rate for the forward and backward reactions, you would have too many transitions, and that would be, not very useful in practice. And then finally, the other option that we have is that we have to find the minimal rules. that have these properties, right? That the delta, that the amount of the number of occurrences of the energy terms that are produced and are destroyed by the application of the rule are independent of the context in which this rule is applied. That's what we will try to do in this approach. So to give you an example of how it would work, here we have one rule, and here we have one energy term. Very simple, one rule, one energy term with its energy cost. We call it the triangle, that's epsilon t. And this rule might destroy or not destroy a triangle depending on the context where it's applied, right? I think that should be clear to you. Is that clear to you? Great. So now what we would like to find is a set of rules that can replace this rule, right? Having this, but not changing the semantics, right? We don't have to have more instances or like more matchings on the left hand side, for instance, nothing like that. We want to preserve the number of matches of the left hand side on any situation, on any context, on any.
Sorry, Ricardo, I've heard the audio is not working.
Why was it mute? I mean, I just came back to the window. I said it was muted, but now you hear me, right?
Yes, we can hear
okay.
you.
Until what part did you hear? At what time did I go silent?
I think when you asked if everything was clear. After that, I will not.
Okay. Okay, that was in this slide maybe. So maybe I should.
Yes.
No. It was here. Yeah, right, with the triangle. So it's clear that this rule can break a triangle in certain situations. So this rule does not have this property that we're looking for. That the number of in particular of this energy term will change depending on the context. So we want to replace this rule by a set of rules that that express the same thing, right? So all those rules together just add up to the same thing as having this rule. And that's something that we can do in this type of rewriting because of what I was talking at the beginning of this rigidity. So in this particular case, for instance, here, if the orange node is bound to something, it's bound to a blue node, it cannot bind to another blue node. And if it's bound to a green node, it can only be bound to one. And this kind of rigidity allows us to replace this rule by this other set of rules that you will see shortly. So can you guess here what would be the set of rules that we would need to generate to be able to handle all the situations where the triangle is created and where the triangle is not created? Sorry, destroyed actually, because we're destroying here.
So if I may hazard a guess.
Yes.
So obviously you can overlap the triangle with the rule in the obvious way, so that the sort of yellow node matches the yellow one and the blue one matches the other blue one. And then you know that one triangle is destroyed. And then maybe you need variants of this rule which guarantee that you do not have that overlap. So all the other possible overlaps obviously would not, or even the disjoint situation would not destroy the triangle, but you somehow have to ensure that the other variant specifies that it does not overlap in this problematic way.
Exactly. So yeah, as you said, the computing the rule that creates or destroys a triangle is kind of like the easy part. You just overlap in the obvious way and you get a rule that destroys a triangle. And that's the only one that can destroy a triangle. But then to generate the other rules, the ones that do not destroy a triangle, but help you preserve the meaning of the original rule, right? So kind of enumerate all the possible cases in which a triangle cannot be destroyed. That's the difficult part of this work. So if we use the algorithm or the method that we developed in 2013 to do that, you will get this non-exhaustive list of rules. By the way, something I didn't mention, but maybe it will be helpful later on, is that this rule, we call it the generator rule, and these rules, we call them the generated rules. So yeah, so this is the one that Ricardo correctly described, the one where you break the triangle. And here is a non-exhaustive list of other possibilities, right? In which the orange and the blue are bound to a green on this side, but the green is free, meaning that this green cannot be bound to this orange node. Another possibility is that this node is not free, is bound to something, but it's not the same orange node that we have here. It's a different orange node. Or you could also grow it in the other direction, right? And say, well, the orange node is not free, but is bound to a green node that is free. Or you could say that the orange node is bound to a green node that is bound to a blue node. Right. So here that we are not exactly getting the minimal set of rules. And that is correct. And I only know it because I know another set of rules that is smaller, but I actually don't know, although I'm very suspicious that it is the case, but I don't know if the other set is actually minimal. I think it is, and we will see that now. So for that, there's this useful concept which we call the primes, and the primes are just minimal T-balance extension. So an extension of the left-hand side or the right-hand side or any graph actually is any homomorphism that does not add any connected component. So if it extends the connected components that already exist in the graph. And we say T-balance to say that, well, we've been saying all the time, right? Delta T is known, is fixed, can be computed statically independent of the context of application. That's T-balance. And here the minimal extensions are these ones. Well, this one we know, and we have here one option is to have the blue node free or the orange node free that already makes it sure that there's no triangle involved. Or we could grow it in that direction and say the green node is free, or here in this direction, the green node is free. That also asserts and guarantees that there's no triangle involved, and the other option is being bound to a third agent, right? However, the sort of problem that we have with this whole set is that this whole set does not preserve the meaning of the original rule, right? Because if we put these two, now there's a graph that has both nodes free here, so both sides free actually. This side and this side, right? Imagine having this and this side here free as well, and both of them will map into that graph. So they are not mutually exclusive. Here happens the same, right? And here as well the same problem. Is that clear? Great. So, but then a colleague, Joanna, told me once, you know, that is true, but if you pick a subset of this set, of the set of the prime, you get that mutual exclusivity that you're looking for. And one subset is this one, and the other subset is that one. If we take those subsets, we're good. We are mutually exclusive, we are exhaustive, we cover all cases in which the original rule could be applied, and we do it so hopefully in a minimal way, right? As you saw before, the algorithm that we developed in 2013 generated many rules. This is just 5 of them, but there are more. And here, for each one of them, we would be generating only 4. Okay, cool. What's the problem with that, or the difficulty with the prime? The difficulty is that this splitting of the subcases that the primes do is not possible to be expressed by the machinery that we developed to that we developed in that first paper, right? We used something that was called refinements, and refinements had a particular property, and that particular property was the following, right? So if you ask, we said, if you ask for a site in a extension, you have to, so in one of the extensions that you will keep, for instance, okay, here, let's work with this one. So we have these 4 extensions that we will keep in the result. And you have the original rule, and you add one side here. You add this side, for instance. No, that side actually doesn't work. Let me think. No, actually, yeah, it works for the subset, but it doesn't work for the set, it seems. So, for instance, here we ask for this side, but here we don't ask for that side. And the refinement that we were working with, they guaranteed that you would always ask for that side in all possible extensions that you keep. So then I was like, was that clear? I felt that was not that clear, but was that clear enough maybe? Good. So then I said, well, it seems like, sorry, actually, I made a mistake. I was talking about the machinery of refinements, but actually that was not the name that we used. Refinements are good. The thing that we used to express these refinements, to construct these refinements, were called growth policies, and those were the things that would have this constraint that once you ask for a site, you have to keep asking for a site everywhere. So instead of that, here I will work with a different type of refinement that does not have this property. So let's start with this rule. So this is just the right-hand side of the rule, but you can think of the left-hand side of the inverse rule. And here we have a small refinement, which is just add this site to the orange node. And you can also the site that would go here. And you can, so once you add it, you have to say if it's either free or bound, and if it's bound, to what it's bound. And here we will add the site, this site, the site that would go here.
So sorry, Ricardo, let me just check. So this is really a decision here. So basically these two branches are mutually exclusive because the site here, so the little stick that goes out here, basically means there is a site here, but it's not bound, right? And in the other case, it says there is a site which is bound, so you cannot have both.
Exactly. Yes.
And that because that is a special kind of thing in
this type of rewriting.
In this type of graph, right?
Yes, exactly.
Yeah. Okay.
Yeah, that's the rigidity that we were talking about.
Yeah.
So here, basically in each step, you have this you have mutual exclusivity, right? Mutual exclusive, exhaustive, and this type they are mutual. However, here it's not this. Not in the data construct this refine because this that we ask for here and here. Right. So in our policy, force us to unfold as well. But if we really want the minimum, we can do that. And I with this decision graph. And here the that are there in the original graph. They have.
Sorry, Ricardo. There is some problem with the audio. I don't know if only my problem or for everybody.
It's the same here. So it sounds like a loose connection. So it's cutting out sort of every couple of seconds for a bit.
Oh.
Maybe check whether your plugs are in.
Yeah, I hope the wind is not like making the connection unstable. Is it better now? You hear me better?
Yeah, I think it's better now.
It's better.
Andrea, how is it for you?
Yes, it's better. Now it's better.
It's better. Great. Thank you. So so I've been playing with this graphical notation. So yellow sites are there in the original graph. Red sites are the sites that we are kind of consciously adding, right? And so in each decision, we are saying, okay, let's add this site. And in particular, decision that we make here is let's add this red site. And then only in the case where this node was added, we will add this other red site. That's what the meaning of this kind of semi-transparent white arrow. So add this red side only if you have added this. It's a way to give this dependency, right? So let's say we want to add this side, not on this branch, but on this branch, and we would get this, right? So here we get that, and we do not add this side, but here we add it, and we have only two options because this, sorry, why is it that we cannot have the triangle here? Ah, right, because, oh no, sorry, I made a mistake in this slide. That's why it's tricky. So this green node should not be here, right? And we are extending this thing. That was an error in copy pasting. So this orange node here and here should be free on both sides. Yeah, and I think, no, this is correct. Yes, because the green node can appear here, right? So, and now the dependency is different, right? If we want to add the other side only when this side is free, we put a white arrow from the red side to the red side instead of from the violet side to the red one, as we did in the previous slide, right? Here it was from the violet to the red. Here is from the red to the red. That means only do it when it's free. So those are the two options. And there's another option, which is do it on both branches. And then there's no white arrow. There's no dependency. Like do it anyway. And using that notation, we can express the two set of refinements that are contained within the primes like this, right? The red refinement, we do it like this. And then the purple refinement, we do it like this. Is it clear how that went? Cool. So so what I've shown you is work that I've done several years ago. And you might be wondering, well, but what are you doing now, right? What's more recent work? And well, more recently, I've been working on a implementation of Kappa in Coq that you can find there.
Before we change topic a bit, I had a couple of questions on the previous one, sort of high-level questions. Yeah. So you had those three alternatives that you discussed earlier: the metropolis, then the refinement approach that you showed here, and the other one where you say you generate the whole transition system first and then work it out kind of on that basis. Are they all equivalent, or under which conditions are they equivalent, apart from the fact that one is maybe more efficient than the other, as you said?
So the last two are always equivalent, right? Enumerating all transitions and computing the delta energy for each transition, and making a transition system based on that is equivalent to the approach where we find the refinements, the minimal rules.
Okay.
However, the metropolis case is not always equivalent, right? It's equivalent only in the limit of time. So the metropolis case converges to the probability distribution that we want to converge to, right? Well, in both cases you converge, right? But I'm actually not completely sure, but I feel like in the metropolis case you are converging. You're even converging by rejecting certain steps. You are trying to converge to the real transition, to the real transition rate, right? So I would expect the convergence of the later two approaches to be faster than the convergence of the metropolis approach. But that's just a conjecture. I have no proof.
Okay, but so the equivalence is not in the actual transitions that you generate, but more generally in the limit, as you said. Okay.
Yes, in the limit. Yeah.
Okay.
Yeah, but the other two are by similar, I think. Even I mean, they are very.
Okay.
Yeah.
And the limit is basically the question of what is the. It's basically a question of the limit concentration, essentially. So the limit, the numbers of pattern occurrences for the different terms, or the number of occurrences for the different terms in the. So that stabilizes at some point, and that's basically what the limit is, right? So it's not the actual. So okay. So maybe let me rephrase my question. So if you think of this as a way of calculating some kind of equilibrium in the end, where you have, I mean, like something like a chemical mixture, and you want to work out long term what is the result of the reaction. So that is the limit, and that is the same with all of these three approaches. But the actual process to get there, the behavior, if you like, if you think of this as a behavioral model rather than one which is just computing this equilibrium, then they are not equivalent because they have different transitions.
No, actually, the latest two approaches should have the same transition.
Yeah. Sorry. So the latest, the other two, but they are not. The other two are not equivalent to the metropolis algorithm from a behavioral point of view. Only from the point of view of the limit result, basically of the end result.
Well, that depends. So I'm not acquainted with the term this kind of behavioral thing. So in the behavioral approach, would you say that rejecting, so when you reject a transition in the metropolis case, would you say that's part of the behavior or that's not part of the behavior?
Yeah. So that would be part of the behavior. So if I think of this as a model for a sort of how people operate in social networks, let's say.
Right.
So then I'm interested. I mean, I can be interested in different things, but so I may be interested in the structures that are emerging and in the kind of ratios between the different patterns that I can observe. Okay, so that would be the long-term behavior. So that I understand is the same independently of I mean, with all of these three approaches. But I may also be interested in observing the actions and the actions would not be the same because
exactly.
Okay. So that's what I wanted to understand. Okay, that makes sense. Thanks.
Yeah.
And sorry, can you think of conditions under which this would be equivalent? Is it? I mean, I don't know whether that even has been studied, but because I know that the refinement approach only works under certain conditions. I mean, first of all, the rules were. I mean, not necessarily symmetrical, but had to be kind of cyclic at least, isn't it? So that you can always, I think it's called, if you apply this to Markov chain, I think it's called irreducible or something like that, isn't it? So that you don't have, basically you don't have traps, sort of subsets of states that you cannot get out anymore. So that,
So irreducibility, what guarantees is that you always converge to the same probability distribution, right? Because if it's not irreducible, then your Markov chain has disjoint connected components, and depending on the connected component that you start, you will obviously like converge to a different probability distribution because you will never reach the other, right? The states that are reachable in one are not reachable on the other, and therefore, the probability will be zero. So yeah, that's one thing. But you can always like generalize or relax that constraint of irreducibility and just talk about probability distributions per connected component, right? That's what you really care about, I think. Yeah.
Okay, so that means even this irreducibility doesn't make these three alternatives equivalent in the strict sense. So this is
no. It definitely wouldn't make them equivalent, because in metropolis you will always, I mean, not always. There's obviously, actually no. I don't think there's any setting in which the metropolis case would not ever reject anything.
Yeah,
would have probability one to not reject.
Looks like a kind of greedy thing, at least on the side where you actually reduce the energy. It always takes that transition, right? So it's
yes.
So
yes, and there will always be. I mean, if transitions are reversible, which is a condition that you want to have, then there will always be a direction for the transition that goes uphill, and that you will be rejecting sometimes. So yeah, there's no chance.
Okay. All right, cool. Well, thank you.
You're welcome. So yeah, there you can see a bit more recent work, but it's been slow working on this kappa implementation in Coq. There was the steep learning curve of Coq first, and then now I'm trying to prove the things that I talked about in this talk in Coq. But it's making progress slowly. I'll probably have to do it anyway as part of this research grant that just finished, but that I'm not free of yet. It has to be approved. And that a little bit of acknowledgement and thanks to the people here in these pictures. They all helped me in different ways, and of course there's other people that also helped me that are not here, but well, so it's life. I just made a selection of the people that has helped me, and the funding agency that has helped me work on this for the last 3 years.
Okay, very good. Because I mean, I already asked the question, so if anyone else has a question, please let me know. Otherwise, maybe I have one on the last point that you had on the Coq part. Yeah, Nicholas?
Hi, thanks, Ricardo. I was wondering, in all of this time that you worked on this energy-based modeling, do you have any idea if it would be possible, so if one were to really formulate the Markov chain with a rewriting for the special case of kappa, do you have an idea whether it would be possible to prove a formula for, let's say, the infinitesimal generator of the Markov chain based upon these minimal extensions that would bisimulate the Markov chain, or is it more about the observations that are bisimulated? I mean, when experimenting with this, there are several things that could happen. I mean, I guess what you're saying is more about if you only observe the average count of the pattern, you can derive a similar formula. But did you ever look at this Markov chain formulation?
Yeah. And in fact, the bisimilarity is complete, right? I mean, in the sense that it's not just the observations; it's all transitions are bisimilar. For each transition of the original rule, let's say, you have one transition in the set of refinements, and only one.
So if I were to use my Markov chain tools, I should see that I take your pattern, I take the differential equation which expresses its change in time, and I should see in principle, if everything goes to plan, that if I took the commutator of the pattern with the original rule versus with the refinement, I should get the same contribution in principle. No, I should be able to verify what you said in this way. Okay.
Yes, although you have to right? The original rule, that's something actually important that I wanted to mention and I didn't mention. The original rule is only qualitative, right? It does not have a probability because you cannot assign one. You cannot assign a rate because you don't know what will be the change in energy. So yes, you bisimulate it in a qualitative way, right?
I know. Sorry. I think I'm asking. So in Markov chain semantics for the stochastic chain, you would define a rate. It's just a parameter, and then you have like a definitive change, an infinitesimal change in pattern count. And in Markov chain theory, there's no place where you can define a static energy change for transition, because I mean you would need a reference measure for that. So I think what you're saying is that you have a feeling that maybe instead of picking a parameter for the rate, you seem to say there is a way of choosing, let's say, something like a relative weight or something, which under certain conditions is capable of distinguishing between rules. But so I didn't quite get the link between energy-based modeling and ordinary continuous time Markov chain semantics. Do you have any idea on that part?
So the link is the compiler, right? That transform an energy-based model into a set of graph rewriting rules with a rate.
Okay. Mm-hmm.
So that compiler like maps your energy-based system into the usual semantics, into the usual continuous time Markov chain semantics.
So I think I'm interested in that part. So basically, you are saying you have a system of maybe still you would have some base rate, let's say, for transitions, but I mean, then you dress it with a weight which you compute somehow from these energies. Is that what you're saying?
Yes. Yes, exactly. So you compute the generated rules, and now you have to compute a rate for those rules, and you use the energy function to compute that rate. And there's some freedom on how you can choose the rate, because what's constrained actually is just the ratio between the forward and backward reaction.
Sorry, there's a free parameter per rule.
Yeah, there's a couple of free parameters depending on how you assign the rates, right? Yeah, I mean, we have a model that we use to assign rates that we call the linear kinetic model, and it uses two parameters. It's well, maybe more because it's one constant per generator rule and one matrix per generator rule, and the matrix is t times t, right? It's a square matrix of the size of the number of energy terms. That's one way.
And then essentially there will be a statement of the sort for a given choice of energy patterns. I can compute my extensions. I can then compile an effective rate for the rule that was at the heart of the generation. And then in this way, I should be able to derive an equation that, let's say, the average count of the pattern will be affected the same way by the dressed rule. I mean, the one with the extensions versus and is that written somewhere? Can I read about that somewhere, or?
So I actually have a slide about the linear kinetic model. I'm not sure if that's exactly what you're asking for, but like this is the thing, right? This is how you compute the rate of the rule, and you have these parameters, this constant per generator rule, and here you have this matrix, and you have these constraints on the parameters. That's one way, and then you can. There's bad choice of colors here. Sorry. There's two like, if you wish, canonical, not really canonical, but yeah, two kind of easy ways to pick these parameters. In both cases, you put the constant to 0, and the matrix in one case is the identity, and in the other case is 0 matrix. And here you have the diagonal 1/2 for both matrices. And it gives kind of different, it will give you different semantics, right?
Right.
You-
And I mean, so did you ever experiment with kappa, say, on different implementations of the same model with, you know, either with the fully extended rules versus address rule? I mean, is it something you verified with the simulations that it's working? Or, I mean, is there any, because apparently you don't have a direct mathematical comparison between the two. I mean, I'm trying to see how to get these exponential factors from any sort of the standard tools in CTMC theory. Out of curiosity, just to see how one would compare.
So just to answer your question first, no, we have not tried it in models or simulations because we have no implementation.
Ah.
So the idea of this grant that I'm part of was to actually build this implementation.
I see.
And that's why I'm working on this kappa in Coq thing, and so that answers part of your question, but doesn't answer the part of your question where you're curious about how you could use these, how you call them, exponentials or
well, yeah, here because
so
I mean, part of the calculation one can do in Markov chain theory for stochastic writing systems is computing the rule algebra-based commutators. It would essentially look at how exactly you could look at the before and after overlap of a pattern with a local context of a rule, where I mean, you would basically only select the local and then since it's kappa, all of these partial overlaps can be completed into enough information to distinguish them. So that part I would see. But I'm curious about this way of, you know, defining a rate for a rule based on these energy patterns. And it seems that these rates are really non-trivially dependent. I mean, having these, for example, e to the minus. So that is something very interesting because I guess in biological models, you can't really freely choose these rates. I mean, you don't have often an idea about the parameters. So that seems to be a bit like this estimation. I've seen it only in organic chemistry. You know, you could estimate rates based on static information. So I think that would be quite interesting to see in the formulas, like how it would translate into the, you know, mathematical Markov chain theory. So, but maybe to be discussed more at some point. Yeah.
So yeah, I can say two things I think about that. Oh, I forgot them. Sorry. So the last thing is, yeah, but it's something that I said before as well, but maybe I'm not saying it clearly. So once you do this transformation, right, and you get the generated rules and you apply the whole machinery and you finally will get a rule, like a usual graph rewriting rule with a rate. And that you can use to do whatever you do with the usual continuous time Markov chain semantics, right?
But they're actually, sorry to interrupt.
Right?
It's just to say that when I would look at, you know, the ordinary Markov chain theory, I would have a rule, the minimal original one, which was just linking sides. I could then...
No, the minimal original one would disappear.
And exactly. And then you would replace it with all the local refinements, right? That's the idea.
Yeah.
So,
exactly.
and there's a certain way in which you get a sum of possible options, possibly with weights, depending on exactly what is the rule. But that would give me more like a linear dependence on whichever way the patterns can overlap. I don't quite see how to get this. I would have expected somehow a weight between the different options that a rule can be fired locally, which is something like a partition of like a probability of some sort. But it's to be linear in number of pattern matches that you can have. So, I mean, I'm slightly surprised you can then still have a degree of freedom of choosing the rate you get, because it seems there's an extra step involved which you might have motivation for. But yeah.
Yeah, I mean, the reason why you have this freedom is just because the let's call them the laws of statistical mechanics just constrain the ratio, right? Because if you pick a different one, it will converge to the same probability distribution. But of course, the kinetics will be different, right?
Exactly.
You might converge to the probability distribution much faster or much slower, or
I see.
all sort of things happen. And then of course that's only guaranteed as long as you work with the isolated system, right? But
Exactly.
one
You
of
have
the
the
advantages
equilibrium.
of this approach is that
Mhm.
you can, once you get the generated rules, you do not need to keep them isolated. You can mix
Mhm.
them with irreversible rules if you wish, right? Because there are some things in some modeling situations you really want to express some things that are irreversible,
Mhm.
right? For instance, I don't know, the movement of the earth around the sun, it has a direction, right? And
Mhm.
and you go, like cycles of light and dark because you have the direction. It's not like at each point in time the earth could go further or backward, right? so you can, one of the good things that's not possible, for instance, with the Metropolis algorithm, is that here you get the output of your algorithm, and then you can use those rules in other modeling situations
Mhm. Mhm.
that would
Okay.
not converge to the probability distribution, right?
Right. Well, thanks for now, and maybe I'll let over to Raiko or Andrea to ask other questions. Thanks, Ricardo.
I have another one, if I may. So I can. I'm thinking sort of how much of this. I mean, obviously, this is a method that works precisely in the sense that it, if you're working with these kinds of graphs, with side graphs, or maybe with rigid graphs more generally, and you use these particular refinement techniques, then you get an exact solution. Okay.
Yeah.
I'm wondering if a similar idea is also applicable in situations where some of these conditions are not satisfied. So let's say if you have general graphs, so not rigid graphs, but you only want to use the energy controlled rewriting, if you like, as a kind of heuristic rather than as a precise method. Okay, so
Right. Yeah.
so
Well,
I mean, I can think about the Metropolis algorithm, for example.
exactly.
That doesn't rely on your assumptions about the underlying graphs.
Yes.
And
Exactly. So the
Yeah.
Metropolis algorithm is always an option, right?
Yeah.
If you want to do this kind of statistical mechanics or energy based or energy modulated modeling, you can always resort back to Metropolis, because that's the good thing about Metropolis. It makes very few assumptions about the system.
Yeah. So that alone
Now,
is interesting, because
yeah.
I mean, one can probably think of applications where this kind of idea of energy controlled rewriting is useful, but as I said, which don't have these specific features. So that may be an interesting thing to explore. But the other question then would be, so what would happen if you just or would it be possible to use something like the refinement-based approach to constructing new rules, to constructing derived rules, if you like, in a kind of energy-guided way, but as a heuristic rather than as a method that exactly replicates the original behavior?
I see. Give me a moment to think, and I actually will use this moment as well to take off my glove.
Getting warm in front of your fireplace.
Sorry, I couldn't hear you. It's getting hot here.
Yeah, as I said, you're getting warm in front of your fireplace now.
Yeah, exactly. Like the sun is out now, and the fireplace is not needed. So yeah, so let me think. It's a good question. I like it.
I guess the question is kind of symmetric to the strict case, or the rigid case. Let's say the rigid case with the proper notion of refinement, which allows you to do this exactly. You have you can either use the Metropolis or the refinement-based approach. maybe, but equally, if you have the non-rigid case, maybe you can still do something statically there, which kind of replicates the result that you would achieve with the Metropolis algorithm in the long term, but does so without, as you said, without having to do that computation of the energy patterns all the time.
Yeah, it might be possible, but I'm not. You know, I do not have enough experience with the other types of rewriting.
So I'm just thinking of this as a I mean, think of this as a optimization problem that is not solved accurately, but by some kind of heuristic, basically, so basic way where you're approximating an optimal solution based on a heuristic. Yeah, I mean, it happens all the time in optimization.
So how does that work? How do you use graph rewriting in other contexts?
Well, I mean, I don't think I have precise examples, to be honest, but I mean, one thing we discussed at some point, I think in a similar context, was how to generate graph transformation systems, essentially, from higher level requirements.
How to generate graph transformation systems?
Yeah, from kind of high level requirements. And the idea maybe is that you have the setup is a bit similar to what you said. So you have a set of basic rules, let's call them generator rules, which describe everything that is physically possible. Okay. Yeah. And then what you want to do is you want to generate those rules that are actually likely to be applied. Yeah, if the assumption is that your system is kind of somehow minimizing some objective function, and the objective function could be, for example, something like an energy function. So some kind of expression, maybe just a weighted sum, as you showed it, of pattern occurrences. But I mean, potentially it could also be something more complicated. But if you stick to that you have essentially energy levels for each pattern, then you have a kind of weighted sum, which you can then use as an objective function as a kind of optimization problem. Okay, and then you can look at this in a dynamic way and say, I have my basic rules which describe my solution space, my state space, let's say, and then I'm searching for a solution that is minimal with respect to that objective function. So that would be, I guess, the Metropolis algorithm would be one possible heuristic for that, for solving optimization problem. But you could also think of solving this statically, as in by refinement, where you're trying to pre-compute the rules that are likely to lead you to that optimum, by basically sampling or trying out, for example, all the possible refinements of rules, so embeddings of rules into context, or by trying out possible rule compositions even, by sort of concatenating rules. But then, of course, you have the problem that you need to evaluate what is the effect of this rule on the objective function. Because obviously, if you cannot work this out precisely by means of the refinement, you have to, I mean, either estimate this somehow, or you have to work it out by basically running your system and then actually measuring this or calculating this. Let's say, what is the average effect of that composed rule or extended rule on the energy, looking at the states when you apply the rule. Okay, so that was kind of so in a sense that would use a similar philosophy, but do it in a heuristic way without having to assume these very specific requirements that you have. Which, as I said, I'm sure there are applications where the idea or the metaphor of energy is useful, but the actual precise constraints on the notion of graph are not always satisfied.
Yeah, I think that the optimization problem that you're talking about is equivalent to the energy minimization problem, right? That basically here with the Metropolis algorithm or the other techniques, we are doing just that. We're trying to find the minimum of a function. But I understand that you want to that your question is really about whether they are like approximate ways. Oops, whether there are approximate ways to do that sampling. And I'm not very familiar with that literature, but I think there are. For instance, while I was working on this presentation, I went to the Wikipedia article about the Metropolis hasting algorithm, and on that article there are links to many other sampling methods that have actually some advantages over the Metropolis case, because one of the problems, you could say, with the Metropolis algorithm is that you have to pick a starting point, and that starting point will determine the speed at which you converge. So if you are really unlucky about the starting point that you pick, it will take you a long time to converge to the probability function that you like.
Sorry, by starting point, you mean the initial state of your system, basically.
Yes, exactly. Yeah. Yes. So there are other methods that do not have that problem, and I do not remember now the name, but if you go to the Metropolis hasting algorithm in the Wikipedia page, it will send you to other kind of sampling methods that are there exactly to trying to do this. You're trying to optimize a certain function. Plenty ways to do it. Yeah. Now, the interesting thing, and probably there exists no literature, is that you want to take one of these methods and apply it to a non-rigid case, and somehow leverage your knowledge about how these graph rewriting systems work, because that's really what we did here, right? We leveraged the precise way in which this type of graph rewriting works to kind of, I don't know, push down the stack this optimization problem and really get to, you know, it's like a marriage between like rules and energy functions. Like you push the rules to the rules, and that somehow changes the rules. It's yeah, that would need, I think, a lot of I mean, I think you would have to do it not for the general case, but to a very specific non-rigid case. And for me, I still, and this is a question I have for you, Rico, or maybe also for you, Nick. I have troubles imagining what a non-rigid graph rewriting system would be useful for, because for me, like the rigidity is very natural, right? This kind of refinement, mutual exclusivity you make. It's like it works even if you're just talking about ideas. You get an idea or a sentence, and you make it more detailed. Okay, now there's more detail, so your sentence applies to less cases. But you can, of course, formulate these sentences that apply to the cases that you did not cover by the detail case. It's a very natural process, right? It's something that I have trouble thinking does not happen.
Well, but on the other hand, if you have like a dynamical graph system on a sufficiently large graph, and large is already, I guess, a few hundred vertices, you have certain statistical regularities in the graph, and I guess you would replace strict rigidity with sort of approximate, basically you would have more likely contributions that dominate the behavior. So I would imagine that this could still work, but I mean, again, depends presumably on the kind of graph you're looking at and how long in the evolution you want to model the procedures.
I mean, just on the first question, I mean, it's clear that there are graphs that are not rigid and that are useful and interesting. So, and it's clear, obviously, that being able to do refinement by sort of neatly separating out different cases, as you say, is also a very natural thing to do. So, but I mean, it's also the case, obviously, that you cannot always have everything you want. So, my suspicion there would be, I mean, one thing that occurred to me now. I mean, I'm sure we observed this before, is that there may be other ways of defining refinements in non-rigid graph rewriting. If you have,
for example, we have, for example, this polynomial jump closure phenomenon. If you take a rewriting system, you look at how patterns get affected by rules. You might find a subset of possible graph patterns, including, of course, that original one, such that exactly the change in that pattern counts of, the subset of patterns is fully described by just looking at the ways these patterns can interact with the rule. So it's a bit like a generalization of what you wanted, that you can do the refinements. There's a way of looking at sets of patterns that communicate, let's say. So for example, we have a very crazy thing in the Remy generator for planar rooted binary trees. You can describe it as a writing system. Turns out there are subsets of, let's say, 4 tree patterns that in one step of the generation procedure are changed in definite ways, so that you can describe the entire change on the distribution as a shift vector in these patterns. And I think that would be the closest. Then again, of course, planar rooted binary trees are rigid, but we have other examples where it's not rigid. So, I mean, my feeling is it would be nice to understand this procedure and compare it with these cases where presumably your approach would say there is a way of refining the rules that covers exactly those patterns and maybe even allows to identify which patterns would communicate. So, I mean, it's interesting, but I think it warrants like looking at the mathematics a bit closer, maybe for the Markov chain generator. This could work. I mean, I have a rough feeling it could work.
So my other sort of suggestion was, and I'm not sure whether that has been studied before, but if the graphs are not rigid, and you cannot, so my instinct is, and I was trying to confirm that earlier, that these sites that are not connected act like negative application conditions.
Yes, exactly. So if you have negative application conditions, you have rigidity, right? It's actually
no, not necessarily. I mean, you can model.
Let me say something.
If you have graphs or graph patterns with negative application conditions, you can model rigidity, but you have situations where you may use negative application conditions, but still, even with those conditions, the kind of rigidity condition, like in the embedding condition that you have there, is not satisfied.
I mean, actually, kappa in coding of graphs with application conditions versus organic chemistry coding of graphs with application conditions. So very similar structure, but yeah.
No, but sorry, what I mean is that if you're looking for a refinement mechanism which essentially distinguishes cases, which says I can either attach something here or I can make sure that nothing is attached.
Yeah.
So making sure that nothing is attached or not. I mean that either something is attached or that something is not attached. Basically, if this is your distinction of cases there, so that you can explicitly formulate using a negative application condition, even if your graph is not rigid. So I don't know whether that is all you need in terms of the mechanics. There may be something else going on, because maybe in the end you still rely on this unique extension property, that if you have a partial match, then it's either uniquely extended to a total match or not at all. But certainly this idea of refinement by case distinction, that can exist if the patterns have explicit negative application conditions, even if the graphs are not necessarily rigid. Yeah, so that was just my observation there. But as I said, I don't know whether that's enough, because obviously there are other subtleties here. And I think some of this had to do with preserving the number of matches as well. I think that was the uniqueness of the matching, I think, was important for preserving the number of matches of patterns in refinements, isn't it? Which was a very specific thing, I thought, that requires rigidity, which in general you don't have.
I don't think. I'm not sure what you mean by the uniqueness.
I think it just means that if you take a vertex and extend it into a match of the pattern, there's one way to do that or none.
No, but I don't think that's necessary to do this kind of thing. No, I don't think that's necessary. In fact, they kind of. In fact, what I'm trying to formalize in Coq is not actually kappa, but a generalization of kappa that does not have that property.
Okay.
So I hope it would be true.
Okay.
But the point you're bringing brings to me two questions. So on one hand, there's this question in the air of what do we mean by rigid, right? And I know you, Rico, have a paper about rigid graphs. But there's something I'm not sure I do not understand about that formalization. Is it for me the essence in a way of rigidity is this diagram here, right? You see it?
Mm-hmm.
Mm-hmm.
So whenever you can have this kind of decision, like replace this by these two, replace this by these three, which can be done whenever you have a negative application condition. That for me is the essence of rigidity, or at least of the rigidity that I need for doing this kind of techniques.
No, you're actually using that once you know the information shown. There's no alternative. I mean, so basically you are guaranteed when you notice that at the red vertex there is no outgoing edge. Then this is literally, I mean, that is the data you have at that vertex, and that's it. But I mean, you, for example, if it's not a rigid graph, I mean, let's say you only knew it was if it was a multigraph, you could have further outgoing edges, maybe, just not on that part. I mean, there's a lot of things that are magical about this kappa version of rigidity, because you basically really can list the finite number of local extension, let's say, while in a non-rigid graph, you would have many options. Maybe you can fix some of that by asking for a simple graph, but I mean, it's you know.
Maybe what you need is that it is finite, but maybe not. You don't need uniqueness. But we're coming back to the same question. What we mean by rigidity, right? I think the definition of rigidity that Rico is talking from is a bit more strict than what I need for this technique, right? Possibly, what I need is just negative application conditions. In fact, in the case of negative application conditions, this problem is trivial, right? You have the triangle and you just create two rules, one in which the triangle is created and one with a negative application condition that says do not break a triangle, right? It's very simple. So,
and if that is all if that's all that's needed, I mean, that would be a very interesting observation, because that would actually make everything a lot simpler.
In fact, you get that one automatic if you
conditions is trivial.
Yeah, but that is exactly what happens, for example, in chemistry, in organic chemistry, in this coding with rules, with negative conditions. It's exactly that you discover that because you ask simplicity, you can only add that edge if it wasn't there before. And so that automatically then in the commutators makes you for a term where the rule is applied in the version where it isn't present, the edge, and one where it is present. So where you cannot apply the rule. So in that case, I mean, there's certain I think it would be worthwhile trying to compare it to this commutator condition, but I mean for rules with conditions, because that's the more natural setting. And I think exactly, maybe you could at least test whether your approach would work for organic chemistry, because that is exactly not a rigid case, but it's also one case where a vertex must have a certain definite neighborhood. So it's maybe close enough. But I mean, for example, you can have alternative neighborhoods even if you have partial information. I mean, think of a carbon atom which is linked with just one. You only know about one link, then there's still several alternative options. But it's not that you have a completely free specification. So, I mean, I agree. It sounds like maybe for organic chemistry it should work, because the chemists have a version of estimating rates from structure in the reaction. So it would be interesting, I think.
Okay.
Should we maybe close the YouTube stream for now, and then we could stay for a moment. So I just quickly want. So thanks a lot, Ricardo. Very nice to hear the talk. For everybody still on YouTube, you could join us for a quick chat on Zoom if you wanted. The link is still there. And we'll be back in 2 weeks with David Sprunger, who will talk to us about rewriting of, what was it? Rewriting for monoidal closed categories.
Mm-hmm.
Thanks a lot.